All right, important thing to remember here, the domain restriction on arcsine and arccosine and arctangent functions. We already talked about it several times, but it's worth mentioning again because it's a big thing. So the important thing to remember that we can only feed into inverse sine and cosine functions value for x between -1 and 1. The values outside this domain will not work because they're simply going to be not the cosine values. For the tangent, it's from -infinity to infinity. Now the output, when you take the sine of x and then invert it, take the arcsine of x, will it be equal to x? In other words, are those functions inverses of each other? Yes, but only if x is between -π/2 to π/2, like we mentioned before. And for cosine, it is true only if x is between 0 and pi. And for tangent, it's only if x is between -π/2 to π/2, same as sine. So here's a question, a tricky question. Is it correct that inverse sine of x is always x? And the answer is no, it's not always true. It is true only when x is from this interval. Okay, so for example, here we have a sine of inverse sine of 3π/4. So if you look at the unit circle, again, 3π/4 is right here, right? So its sine is square root of 2/2. It's right here. But when you feed that value of the sine into an arcsine function, is going to give you this value, this angle that has the same sine value. So it's gonna, so from 3π/4, it's gonna switch to just regular π/4. Just because of the domain restriction. So keep that in mind when solving problems or answering questions involving these types of expressions. So for example, let's take a look at the following examples. For question A, we have an inverse sine of π/3. So π/3 is this in the domain of the arcsine function? I mean, in the range of the arcsine function, and the answer is yes. It's on this side of a circle from -π/2 to π/2, so no problem. It's just π/3. Now, what about the inverse sine of the sine of 2π/3? Well, 2π/3 is outside the inverse sine range, right? 2π/3 is going to be right here. So that's the angle. So and the sine there is square root of 3/2. So which angle is going to be the corresponding angle that has the same sine value? Well, that's π/3 on this side. So the inverse sine of the sine of 2π/3 is still going to be π/3. Now let's take a look at inverse cosine of 2π/3. So the question is 2π/3 in the range of the arccosine function? And remember, the range for the arccosine is this half of the circle. And yes, 2π/3 is here. So we don't need to adjust anything. It's just going to equal to 2 pi over 3. And what about the inverse cosine of the cosine of negative pi over 3? So negative pi over 3 is going to be down here, and it's located in the side of the circle that's not in the range of the arc cosine. So we have to find the angle that will have the same x value, but will belong to this part of the circle. And obviously this is a positive pi over 3. So that equals to pi over 3. So in the previous example, we saw how to solve the problems where these match, right? It was inverse sine of sine and inverse cosine of cosine. Now they're not matching. So the cosine is inside of inverse sine function and vice versa. So here's what the book proposes to do. The algorithm that the book suggests is if x is in the interval from 0 to pi, then the inverse sine of cosine of that angle is going to be pi over 2 minus x. And if it's not in that interval, notice that it's the range for the inverse cosine. So it matches the range, kind of like of the function inside. Then find another angle in this interval such that y equals cosine x, and then take the inverse sine of that angle, and it's going to be, so it's the angle y now, and it's pi over 2 minus y. Now for the second type of expression, so if x is in the interval between negative pi over 2 and pi over 2, then the inverse cosine is going to be pi over 2 minus x. And if x is not in the interval, then we're going to find another angle in the interval which has the same sign, and then the result is going to be pi over 2 minus that angle. So you can follow this algorithm, or you could just, do the direct evaluation, which is honestly my preferred method. I don't memorize this algorithm, so I just look at what I have and go from there. So what does it look like? Let's actually practice. So we have a inverse sine of cosine of 13 pi over 6. So figure it out by direct evaluation. So what do I mean by that? So inverse sine of cosine of 13 pi over 6. Well, first of all, 13 pi over 6 is outside our 2 pi range, right? So we're gonna do 13 pi over 6 minus 2 pi to find a coterminal angle. So that's going to be 13 pi over 6 minus 12 pi over 6, and we are with end up with a pi over 6. So basically, this cosine of 13 pi over 6 has the same value as cosine pi over 6, right? So that's what we're evaluating now. So what's the cosine of pi over 6? So we know that it's going to be square root of 3 over 2. Now, next step is to take the inverse sine of a square root of 3 over 2. So which angle gives you a sine of square root of 3 over 2? Well, we know that it is pi over 3. So we're going to have pi over 3 as an answer. So that's direct evaluation A. Now, B, let's apply the method that was described previously. So this is what it says. This is a situation that we have right now, right? But however, X is not in the interval from 0 to pi. So we're going to find another angle in the interval, find such as cosine y equals cosine x, and then apply this formula. So here's what we have, and we have to find a cosine from 0 to pi in the interval from 0 to pi that will have the same cosine. So we know that cosine of pi over 6 will be the same as the cosine of 13 pi over 6. So then we're going to say that this equals, they said pi over 2, right? Yeah, pi over 2 minus that angle, pi over 6. So we're going to have multiplying both the top and the bottom by 3. We're going to get 3 pi over 6 minus pi over 6, which gives us 2 pi over 6. And when we simplify the fraction by a factor of 2, we're going to get pi over 3 again. So we did get the same result in both ways. So basically, it's up to you whether you want to memorize the algorithm or just want to go ahead and evaluate it.